recording. All right, very good. So the recording has begun. As I said in lecture the other day, I encourage you to interact with me just as much online as we do in class. It's a little bit different, without having the face-to-face contact. It seems a little more distant, but that's why we just have to try a little bit harder. So number one, of course, you can chat with me as we're going through class. Don't think you have to raise your hand and then write something into the chat. I can watch the chat window and I can watch the lecture. So I know if I know if you've said something to me. So don't worry about that. And if you want to talk, that's no problem as well. I mean, I encourage that. The only thing I do ask about that, and this is where it becomes a little bit more difficult, is keep your microphones on the mute. So mute your microphones if you're not going to be talking to me, and that's only because of the background noise. It becomes so becomes distracting sometimes. I don't know if you've ever been on conference calls online, that kind of stuff, or whatever, or webinars. Sometimes if someone doesn't have their mic muted, you hear everything going on in the background, and it just seems to be more distracting online than it is, in what was I going to say, in person kind of thing. But by all means, please turn your microphone on if you do want to say something. Don't think that I want you to stifle, talking to me. And again, you can always chat. Speaking of background noise, my microphone, of course, obviously is on. I have 3 dogs, and occasionally they go crazy in the background because somebody comes to the door, or God forbid somebody mows the lawn or something like that. So if that happens, occasionally I may have to mute the mic for a second and go calm them down and get them back on track so that we don't have to listen to my dogs barking in the background. You can also write on the whiteboard, all right? So this thing here is obviously the whiteboard. It's basically just the slides that we saw in class. Now I can write on it, so I generally don't try to word already. It's not very good. It's a little difficult to write on a slanted surface as my tablet surface is. So usually if I'm going to type a word out, especially if it's something I want you to, something maybe unfamiliar, I usually type it into the chat box so you can actually see the word. So I use this a lot for kind of pointing stuff out, oops, here we go. Pointing that out. But you can do that too. You can also take your pen or your finger or whatever, and you can also draw. Oh, okay, good. Maybe the connection just got better because I didn't do anything. Oh, I'm glad I'm glad. Perfect. So, and I can point, but you can do all that too. I can actually use this little tool up here and I can point. As you see there, and then we're talking over here. You should see like a little hand pointing there. You can also do that. So, and of course, in the middle of lecture, I don't necessarily want you kind of scribbling all over the page, but if you wanted to say, hey, can you go back to that slide and talk about whatever? And I'm like, I don't know what you're referring to. Say, I'm talking about this, right? Right there. You can circle it or point to it. You see what I mean? That's kind of nice to be able to do that. Every once in a while, I haven't had much trouble lately with this, but every once in a while, because of internet gremlin kind of things, I'll disconnect. You'll probably get some message that says, oh, good. Says that I just disconnected. Please be patient with that. In my experience in the past, I usually can connect on fairly quickly. Within a minute or two, I'll be right back online. It's usually shorter than that. If it runs longer than that, if it goes on for a few minutes, then and that usually means that, I don't know, maybe somebody down the road ran into the to the wire or to the cable connection from my house. But what I would usually do is once that comes back up, I'll email you guys, let you know what happened, and then on my own I'll record the lecture. Of course, you all won't be there, but I'll record the lecture when I have the chance to, when my connection is back up again, and post that recording. So in essence, I'm not going to penalize you, of course, if some internet problem occurs between here and there on my end. Now, if you guys are having problems on your end, remember I said the library is really the best place to go, although Daniela said she had some troubles today. And then Chantel emailed me and said that they were having troubles with the flash player on the computers there. But nonetheless, okay, if I do not say something about, okay, I'm going to start the recording now, or the recording is about to be started, if I don't say those words, please remind me. I have in the past occasionally went through an entire class only to find out that I didn't hit the record button, which is awful. So it's if I start lecturing on the material and I haven't said something like, Yeah, okay, I'm gonna turn the recording on now. Please remind me. I've got it on right now, so you don't need to remind me today because I'm recording all this. Remember during what I said about in class on office hours. If you come to see me on office hours, especially on Wednesdays and Thursdays, well, on Wednesdays and Thursdays, this is where I will typically be. If I'm not in my office, like I said, I will be online. It'll look, be the same thing you see right here, just be a blank screen. Okay, after the class is over, it takes a little while, sometimes up to a half hour or so, but then it lets me know that the recording is ready to be posted. Of today's class, I'll put that up on Blackboard as soon as that's available to me. So I try to welcome everybody when they comes in when they come into class. But if I miss you, it's only because I can only look at the chat screen or the participant list screen. I can only look at one or the other. I can't look at both. So if I'm trying to watch to see if you're going to type something to me, I can't necessarily see who's coming to the class. So I think that's all I need to say or that's all I have to say when it comes to that. Does anybody have any questions for me before we get into the material? And again, those questions, Blackboard, mastering, the material we talked about in class the other day, anything like that. Anybody have any issues or things that we need to discuss before we actually talk about biology or marine biology? There is sometimes a little bit of a lag in a chat, so if you respond to something or you ask me a question, it seems like I'm taking a while. It might be simply because it's taking a while for the little hamsters to spin on the wheels fast enough to relay your message to me. All right, so I don't see anything coming in, so I'll go ahead and get started with the lecture material. I'll back up just a little bit, talk about these oceans. Remember, we were saying that really the world is one, it's all one ocean, and what you call an ocean and what you call a sea. I've had that discussion like with folks. Why is it the Mediterranean Sea, the Atlantic Ocean? It's kind of a size thing, and then there's the Black Sea and the Red Sea. So it's kind of like a sea is a little smaller ocean, but it all depends on where you draw the line. But the big five oceans that we think about, and the Southern Ocean, really, the Antarctic Ocean, is sort of just the southern end of all these oceans. Well, so the Pacific is the biggest of all of them. The largest ocean took me 3 weeks to a month to go across when I was in the Navy. So it's beautiful, beautiful water, dark blue water. Except off Hawaii, the water in Hawaii is turquoise, and it's gorgeous as well. Magellan sailed across the Pacific in 1520, which took probably, I don't remember how long. I read a history of Magellan one time, but I don't recall how long it took, but it took a long time. And unfortunately, as we're going to learn in later chapters, one of the reasons it took a while is Magellan had discovered, if you will, what we call the doldrums. The doldrums are the wind currents near the equator that don't blow very fast. There's not a lot of wind there. So the poor guy, you're sailing, and the wind's barely blowing. It's going to take you quite a while to get across the ocean. The Atlantic is smaller, okay, but what I always think about the Atlantic is it's rougher. It's a meaner place. Not that the Pacific can't get mean. I've been out in 40-foot seas in the Pacific before when I was in the service, but I know in the Atlantic that tends to be a little more commonplace. I haven't done a lot of sailing in the North Atlantic, mostly down around the tropical areas around here in the Gulf of Mexico, thank goodness. But the Atlantic was the big roadway, remember, between us, old world and the new world. Because, I mentioned in class, because of the way the Gulf Stream flows, very conveniently flowing east to west from Europe to the New World, and then curling back around and flowing from west to east, going back towards England, right? So the ships could just, not only did the winds blow in that direction, but the currents. And the Gulf Stream is a pretty strong current. If you've ever done any scuba diving, like off the east coast of Florida, you can get in some pretty dramatic currents, and that's just the edge of the Gulf Stream. So these things can move you along at a pretty good pace. Indian Ocean, I mentioned the other day, smaller than the Atlantic, not as mostly in the southern hemisphere, not as deep either. And my recollection of it so much is that it was very much greener. The Pacific is blue. The Atlantic is kind of a gray blue to me, and this varies as to where you are. It's not gray blue off Siesta Key, that's for doggone sure. But the Indian Ocean always was greener to me, and I have not seen the Arctic Ocean. But Arctic Ocean, remember, is covered by Arctic ice. There's no continent in the Arctic, recall. Only Antarctica is a continent. right? And then, of course, as I mentioned, there's the Southern Ocean too. Okay, the Pacific Ocean has the deepest areas too, like the Challenger Trench, 11,000 meters, and we talked about what pressure is and how much pressure that you would experience at a depth like that. Look at that. You could put a Mount Everest in there, and yet still be below water. And I told you in class, think about it as on the surface up here, looking down at the bottom of the trench. It's like when you're flying in an aircraft, right? Then we calculate 11,000 meters being about 35,000 feet. Think about it. So next time you're in a plane, I do that. I look at them and I'm like, my goodness, can you imagine? Can you imagine? Like, you can't even, with 35,000 feet, you can't pick out anything. You can't see a car unless you got like $6 million man eyes, right? You can't see a car. You see just basically vegetation. You don't, you might see, I'm trying to think. Yeah, you might see roads and stuff, but you don't see much detail. Think about how far down that is. All right. Okay. Man, I tell you, you just can't imagine the guts it took these Polynesians and these Micronesians, and the other part is Melanesia. Unfortunately, I covered it up, but that says Melanesia. These are the three sort of oceanic areas in the Pacific. But you can't imagine the guts it took for them to sail out across these huge, wide expanses of water, folks. I mean, a lot of times early exploration of the oceans involved folks that kind of did their exploring near the coast. That's why here in our next slide, or the next slide after that, we talk about all the stuff that was going on in the Mediterranean. The Mediterranean, again, is a sea, right? A little bit smaller. You're not outside of land for too long a period of time. And oftentimes what they did is they just kind of hopped down the land. They stayed within sight of land. But these folks here going out in the middle of the ocean. Now keep in mind, like, for example, where is it? Pitcairn Island. See that right there? Pitcairn Island is where, oh my goodness, the mutiny of the Bounty, the sailors who committed mutiny on the HMS Bounty, which was a ship that went over to Polynesia to collect breadfruits. Holy cow, I'm trying to remember this from my botany class. The fellow who taught my botany class had done a lot of his work over in this area. But anyway, we're not talking about naval history here. Pitcairn Island to Easter Island is on the order of about 1,000 miles away. And Hawaiian Islands, what's that, about 2,000 miles away from this area right here. You can see the dates. This group of people called the Lapita moved out from Micronesia, Melanesia, into Polynesia about 11,000 years BC. And then about another 1,000 years, they had moved into French Polynesia, Tahiti, Fiji, all the areas like that. And then in another 1,000 years, so it took 1,000 years if you think about it, but 1,000 years they were able to make that trek, that 1,000 miles to Easter Island. Actually did it much earlier to Hawaii, probably because of more favorable currents. And they did it, as they said, with these stick maps. And remember what I was saying, what these stick maps are the rocks or the shells represent, say, islands or other major significant landmarks. And the way the sticks are arranged are not only routes, but they're also the way the waves flow or the current wave pattern. You see how like this one's slashed like that. Now, what good is that? Well, these guys were so good. Anybody else having sound problems? Give me an emoji or some sort of a chat to let me know. On my end, everything seems okay here. You still got good connection on my end. Okay. Amy, are you, did it? Okay, Sean, thanks. Okay. All right, so I don't know if Amy's back on yet, but we'll go on. It is recorded, like I said. So you think about these guys sitting in these open boats, and that's what Thor Heyerdahl, that's where I finished the other day. That was a significant. He wrote a book. It was a very popular book when I was a kid. It was about, going out on this adventure. I mean, this guy builds this balsa raft to show. What he was trying to show was that the people in Polynesia may not have come this way from the west. They may have actually come from South America, from the east. And he wanted to show that it was possible with technology that was around, back then, this balsa raft and this kind of thing, that you could actually make the route. And he did. He did actually complete the expedition, and he wrote a book about it. And, he proved that it was possible to do that. So what's that? According to 7,000 miles, right? He proved it was possible. But as I mentioned in class, later on, as DNA evidence became more prominent in science, we found out that that indeed the people of Polynesia were more alike the people from Micronesia, Indonesia, Asia, that area, than they were like people from South America. Okay, so that's what DNA can do for you. You've heard about those things. Yeah, Amy, I saw that. Well, she didn't sign back in yet. But anyway, Amy, are you back on? She's joining. Okay. So that's the beauty that science does. You've seen, or DNA does, you've seen those TV commercials, 23andMe, you can send in a sample of your saliva, and it doesn't tell you, oh, you're related to King Tut or something like that, but it tells you, oh, your people are of Egyptian heritage, and mix them with a little bit of Italian. So that's how they do that. So they take some DNA from people in Polynesia today and some people from South America, and they compare them, and they go, the people from Polynesia are more like the people from the Indonesia. So I'm not saying that some folks didn't, go the way that Thor Heyerdahl thought with his Kon-Tiki raft, but the overwhelming majority came the other way. Now, what's interesting about this is in my Bio 2 class, I talk about something called island biogeography. So island bio, don't worry about retaining this right now. I want to show an interesting similarity that kind of dawned on me today when I was looking at these slides. Island biogeography explains, for example, why Darwin's finches, these are the birds that are found on the Galapagos Islands. And the Galapagos Islands, like the Hawaiian Islands and other islands, are called an archipelago. Now, that is something I would like you to know. Did we talk about archipelago the other day? I don't think so. What is an archipelago? We say something like the Hawaiian Islands is an archipelago. What do we mean? It is a term that we'll discuss as we go through class. So oftentimes when you see the word, archipelago, you'll see like islands. Okay, so Hawaiian Islands, Galapagos Islands. It's a group of islands. Yeah, there you go. So what happens in island biogeography is organisms from the mainland, in this case we're talking about humans, but it could be birds. So organisms, a bird, a finch from the mainland of South America may have made its way over to the Galapagos Islands. Now, that's far offshore, and chances are most of the time you won't make it if you're a finch. Most of the time, if you head out across South America saying, the heck with this, I'm going to the Galapagos, you ain't going to make it. It's right about at the end of the ability of the bird to make it. Maybe the bird that actually, or the birds, the few birds that did make it out there the first time, may have got some wind from a storm, like blowing them a tailwind. The egrets, we mentioned, been doing too many classes. I can't remember what examples I've used, but the egrets, the little white birds that follow the cows around, they came over from Africa to South America. We think maybe aided by a tailwind or something like that. Okay, but what we find out is that once these organisms get onto these islands, if there's an archipelago of islands, then they can spread out. And in a bigger way, you're kind of seeing that here with humans, right? The humans moved from the west to the east, 11,000 years BC, settled around Samoa and Tonga. Took about 2,000 years before they headed down to New Zealand. A lot of times it has to do with prevailing currents. If you're going against the prevailing currents, it's probably going to be, if you're drifting or you've got a sail, but you're basically at the mercy of the currents, you're going to find those areas down current faster, right? So if you got to sail up current from Tonga to New Zealand, that's going to take a little longer. So very quickly out in the French Polynesia, and then not so 300 years till they made it to the Hawaiian Islands. Much longer to the Easter Islands. But these guys would be in these open rafts. I don't know if it was just men. It probably was women as well, using these stick maps, looking at the way animals were swimming, looking at the way the waves were coming, checking out the stars, looking at the prevailing weather patterns. Can you imagine? These guys are like Tom Terry weathercaster on steroids, man. These folks they know by looking at all these subtle little cues. Now, I got a real cool feeling for that when I was in the service. As I remember, we're out in the middle of the Pacific, going from California to Hawaii. We're sailing, and Hawaii is, oh, I don't know, I can't remember exactly, a day and a half away or something like that. And I start to see birds, and I'm like, wow. Now, you know, you don't think about that until you remember that in between California and Hawaii, I didn't see a lot of birds. That's a pretty good way to fly. So, you know, what is going on out here with these humans being able to traverse these long distances are just the one of the prizes of the human brain, being able to take in all this information and use a stick map to go around in these areas in the world. Nobody in the, you know, how many of you would take a, you know, say a 21-foot Boston whaler or any kind of boat? How many would take that from, say, Tonga? Here's Tonga to French Polynesia. I mean, it'd be a cool trip, but whew, you better know what you're doing. Now, numbers tell us, we know for a fact, and this happens in birds or humans, most did not make it. What you're seeing here, the fact that these folks have made it to these distant areas, as indicated on this map, represent the successes. Remember, it's time, lots of humans, if for every human that made it to some far-off island, you know, there were probably thousands that didn't make it, just like with those birds, okay? So none of this is easy. Be cool, but none of it's easy. I'd love to do something like that. Okay, so now we jump into some of the early Western navigators, Western talking about folks in the European area. And here's where the Mediterranean Sea, right? The Mediterranean Sea, the Phoenicians began or arose from the eastern side of the Med, Syria, Lebanon, these areas over here. And as you can see, the red areas, they moved their way out through the Mediterranean Sea, but a lot of it was right along the coast, wasn't it? Just like I was saying. So they really never moved too far inland either. They just kind of dominated the Mediterranean coastline. They also moved into the Red Sea, and then they, you know, obviously there was no canal there at the time, but they made their way down from the Red Sea into the Indian Ocean. The first ones to actually make it around Africa. So, I mean, we're talking 2,000 years BC, so that's you know, that's pretty good in terms of not only navigation, having the kind of ships that could, because man, it gets nasty around the southern tip of Africa, right around the Cape of Good Hope, right? Cape of Good Hope. It's like again, it's like the North Atlantic, and in some cases they actually made their way up around the Iberian Peninsula, up around Spain. Come on, pen. Okay, just quit on me. Oh, got it. This way, right? So, you know, even though they stayed pretty much kind of inside of land within the Mediterranean Sea, there were plenty of them that had the stones to go out into the open ocean. So I would presume plenty of them were just as good at navigating as some of those Polynesian folks were, because when you get out in the open ocean, it's a little different. You don't got land to sight from. Or if you're out in the open ocean in the Med, you're thinking, well, as long as I stay straight, keep the sun and the stars in the right position, you know, I'll eventually get from, like, say, this spot to that spot, you know. Okay. Does that make sense? So we're going to stay, you know, close to land. But as people are getting better, we're going to move out. So one of the things we need to know is where we are. That's always important. Especially as folks, as you see down below in 450 BC, this is Herodotus, and then Ptolemy's map. Especially people started making maps. What sense is a map if you don't know where you are? You know, like when you walk into a mall or something and it's got all the stores that says you are here. Well, what if it didn't have the you are here? You never been in this mall before. It's kind of useless. I mean, you might be able to figure yourself out, but you know, without some way of knowing where you are, maps are basically just paper. And the first puzzle that we had to solve was the fact that where we were on the Earth, north and south, or the first puzzle that got solved because it was a lot easier, by the way. So here's the Earth, here's the equator. So I'm talking about where we are, latitude, right? And way back 325 BC, a Greek guy by the name of Pytheas figured out that basically it has to do with the star above the horizon. So you pick a star, like maybe Polaris, the North Star, And like you see that little inset, the little picture right there. At the equator, the North Star would be flat, right up on the horizon. At 45 degrees latitude, it would be, now we're talking obviously about the northern hemisphere. It's going to be a different star in the southern hemisphere. My son went to New Zealand. I said, did you see the Southern Cross? And he's not really astronomy like I am. And he's like, what do you mean? I said, that's the southern version of the North Star. When I was in the service and went into the southern hemisphere at night, it was a cross of stars. It's not one stars. And remember, the shorter part of the cross points to the South Pole. So you could use something like that in the southern hemisphere. And then again, Polaris is going to be above your head at the northern pole, right? So that should be easy enough. It's all, what's that stuff, trigonometry or maybe geometry. And Greeks were really good at that. So they could know by where they were latitude. And then in the southern hemisphere, using the right star, they could figure the same thing. But longitude, that's a different story. Longitude are those lines that go this way. Longitude was actually figured out by the Arabs. It was actually figured out how to do longitude by the Arabs for hundreds of years before we discovered it again. But the information on how to do that, the instructions, if you will, were actually lost when the fire in Alexandria was burned. There was a library in Alexandria that contained all of the works and all the knowledge of the world at the time. About 400 years AD, it was burned, it was destroyed, and all the stuff was ruined. Had to do with about the fall of the Roman Empire. That's when we went into the Dark Ages, by the way. So the Arabs have already kind of figured this out, but we rediscovered longitude. Usually or often was done by what's called dead reckoning, and that's really guesswork. Dead reckoning says, here's where I was today. I'm estimating that the ship has been traveling 5 miles an hour this way. It's been 30 hours, therefore I'm 150 miles in that direction. That means that you got to do a really good job of knowing how fast your ship is going. Okay, and you got to keep in mind that things like currents and how that adjusts the speed. And throughout a number of hours and a number of days, if you're off by just a few fractions, that's going to add up, right? So using the dead reckoning was what they had, but it wasn't a very good job. And there are reports and accounts of ships running aground because they didn't know where they were. They didn't know their longitude. So even off into the 19th century, into the 1800s, even though, like I say, it had already been figured out, but lost in the fire of Alexandria, gosh knows what else was lost, even into the 1800s or the 19th century, they're still trying to figure out a good way to do this. And the final result, and in a couple of slides, the final answer came about in using a clock, and I'll talk about that in just a second. Okay, so we got the maps by Herodotus in 450 BC, but, accuracy, it all depends on how far you went. Ptolemy got everybody excited with his map. Okay, now, let's do a little history here. So longitude doesn't really get figured out until the 19th century. Ptolemy in 150 AD draws a map, this one here. It's got latitude and longitude lines on it. It's easier to see in your book. How did Ptolemy know where to put the longitude lines? Well, that was, like I said, the information from the Arabs. Now, how to determine longitude was lost. So we have a map here, and you can only know your latitude, but you don't know how far you are west and east. Today, it's easy. You pick up your phone, you look at it. Isn't that nice? Okay, so I mentioned the contributions of Arab sailors as well. They dominated throughout the Mediterranean. Very important trade routes. As a matter of fact, one of the reasons why the Europeans, folks up in this area, started trying to find an alternative route to the Far East around Africa was that going through the Mediterranean, then overland and through the Arab area, because the Arabs were in control of that area at the time, that they dominated the trade routes. And when you dominate the trade routes, especially during this time in history, you basically dominate history, right? You see what I mean? They were aided, though, getting to where they were going in the Far East, because they went all the way Eastern Africa, all down the coast, all the way over into the Indonesia, in that area, where the monsoon winds. See, the monsoon winds are the seasonal winds in the Indian Ocean that blow in the same directions. From the summer, they blow from the west. So the Arabs would pick up the wind and it would blow from the west and carry them over to the eastern part of the Indian Ocean. And in the winter, they reverse. So it's kind of like a seasonal Gulf Stream, right? Like I was talking earlier, the Gulf Stream being that circular, this was like a seasonal circle. So in the summer, you would set out your ships and ply across the Indian Ocean off to the east, pick up your spices and all these exotic things and all that stuff that was valued. And then in the winter, when the monsoon winds blew predominantly from the east, blah, 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 you head yourself back over to the western part where the Arab Peninsula and all that is. Look at that Greek trireme. A trireme, this is a Greek trireme. A trireme means it had 3 sets of oars. You see, a lot of the ships back then not only used sail power, but oar power. And the reason why is sails at that time, technology and what we understood about sails were all predominantly square shaped, which works, but there are other shapes. And if any of you have done any sailing, you know that there are more efficient shapes to make sails out of. Okay? So you had to add oars to that. This is where the whole, slaves and the whips and all that, and you're pulling on the oars and doing all that sort of stuff. All right. The Vikings. Now, they're interesting folks. See, while the rest of Europe is kind of stuck in the Dark Ages, the Vikings actually began to move out and did a little bit of their exploring. And, not unlike the Phoenicians, not unlike the Greeks, they stayed kind of within the sight of land, if you will, although they moved out a little bit further. So, for example, they didn't go from the Viking area. They didn't go from Scandinavia all the way to North America. They ended up there, though. But they first headed over to Iceland. Okay, so what is this? 860, the year 860, and this is going to be some of the very first. And they set up colonies there. We know that from archaeological evidence. That's just a short jump with old Eric the Red over here to Greenland. And then, wow, look at that. Then you're jumping down the coast and you're moving out through the rest of the North American continent. Leif Erikson is credited with the first Viking fella that made its way to actual North America. Vinland it was called, or Newfoundland we call it now. Newfoundland we call it now. Newfoundland. And then they spread out. As a matter of fact, many of them spread out throughout the northern part of North America, ended up, in Minnesota, hence the reasons we have the Minnesota Vikings and in that area. And that's why there's a lot of people up in that area of Scandinavian descent as well, other than the fact that in later immigrations, when folks come to a new area, when they immigrate, they tend to go to places that they're familiar in terms of climate and things like that. So people from Scandinavia, when they came to America, would probably be more comfortable in areas like Minnesota, more familiar with 9 and 10 months of snow and cold and horrible weather. An interesting thing that's come about, what we've learned, what happened to the Vikings, because by the time Columbus and, he didn't really come to North America, but by the time the Europeans made it back to North America in the 15th century or so, the Vikings weren't around. They were gone, okay? So what happened to them and the settlements that we've discovered, although they did last till almost, Columbus is 1492, right? About that little poem that you remembered. And then, so we're talking 15th century, early 16th century. But, they probably didn't contact each other for sure. But a lot of the habitats we found were abandoned around this time because of, number one, poor farming, not understanding the necessity of good farming techniques, and then also climatic cooling. Climatic cooling would have caused more ice to form, right? Which might have provided more of a barrier for a seafaring folks like these guys were. They were seafarers. Now, when that climatic cooling occurred and the ice formed between, if we had a map of the other side of the world, between Russia or Asia and North America, here's Alaska. Okay, when that was formed, that actually stimulated people moving across into North America. All right. Who we got next? Vikings. Now we get into the Age of Discovery. The European. So this is after the Dark Ages and the Renaissance and the rebirth, and we're all, it's okay to be human now again. You don't have to have drudgery through life. Why did Europeans move out across the ocean? Well, there's money, right? Money, trade, wealth, but just to see what's there too. Some of them did just to see what's there, and that's what you gotta love about human nature. Yes, lots of people made money doing this age of discovery, moving out, European expansion throughout the rest of the world. When Columbus made his way over in 1492, when John Cabot made his way over to, just 5 years later, made it to North America. See, Christopher Columbus didn't make it to North America, right? He actually made it to maybe somewhere in one of the Bahamian Islands. I got this little map down here. And Cat Island, I've heard. San Salvador, I've heard. Nobody knows for sure exactly. But he didn't really land on the continent. That wasn't until John Cabot, who actually his name wasn't John. He was a Viking. Yeah, he was a Viking. No, he was an Italian fella, Giovanni Cabot. And then Ferdinand Magellan. He's the first one to circumnavigate, to go all the way around the world. And he did this just 30 years after Columbus. But why was this being done? Well, trade routes, like I said. The Arabs had pretty much put a stranglehold right in this area, so we got to head off this area to make our way to the Far East. Columbus thought, well, why can't we go the other way if the world is round? And because of a calculation from a Greek fella, there was a Greek fella that was calculating the circumference of the Earth, how big around it is. He had made a miscalculation, but Columbus and a lot of people in Europe at the time did not realize that. So when Columbus sailed to the New World, or sailed to where he thought was actually Asia, he thought the world was smaller. That's why he thought when he got to the Bahamian Islands, if that's the place, that he thought he was in that's what's called the West Indies, folks, because he thought he was in that area of the world because of this Greek fellow who made a miscalculation about how big the world was. But he made several other journeys, obviously, to the New World, because even though they didn't find Asia, they found, gold and silver and lots of other things in the New World. Potatoes and tomatoes were New World things that were brought back to Europe. Look at Ferdinand Magellan. So Ferdinand Magellan doesn't make the trip all the way. He is actually killed in the Philippines in 1521, but this is what the outstanding or astonishing value is. They left with 5 ships and 280 men. They returned with 1 ship and 18 men. 18 men, 3 years later. Wow, what an adventure. Now, soon after this, with Magellan was Portuguese, but with Columbus and all that sort of stuff, the Spanish were pretty much ruling the Atlantic Ocean, pretty much ruling the Gulf of Mexico. As a matter of fact, this whole area right off in here used to be called the Spanish Main, and that's because it was the Spanish main set of seaports where gold and all that was being delivered. The British and the French had a different idea. What they decided to do, as well as the Dutch too, they decided instead of really going and collecting the stuff like the Spanish were doing by, abusing the Indians, right? Don't get me wrong. But they thought their idea was to rob it from the Spanish. So that's what they did. They said, the heck with this, we'll just attack these huge Spanish slow-moving galleons, and, they have all that gold doubloon on it, we'll steal the stuff, take the stuff. The Spanish didn't like that, so of course that's where we have the battles at sea that occurred. But in 1588, everything changed. In 1588, Spain lost their rule of the Atlantic Ocean as well as the Gulf of Mexico because the Spanish Armada, which was, oh my goodness, I don't remember. I saw a show about it, but it was a boatload of ships set from Spain to. They were going to go invade England and wipe England off the map and get this English thing over with. Remember the Europeans, they didn't like each other for a long period of time. Was it 130 ships? Just amazing. Yep. And then, but they got defeated, and not even by the English. They actually got defeated by the weather. As they were moving their way up the English Channel, the weather pattern shifted, and they actually couldn't. They were under sail, they couldn't make the maneuver to get to land, so they said, okay, well, we'll sail around the northern part of the British Isles, around Scotland, come around Ireland, circle around again and move in. And when they made their way to the northern end, around the corner, there's the North Atlantic, looking them right in the teeth, sunk most of their ships. So after that, what happens is the Spanish aren't as influential, and the British begin to rise in power. And the British dominated the seas well into the early part of the, or late part of the 19th, early part of the 20th century. Okay, I mean, Britain and their navy was the dominant naval power over in Europe. Well, up until the war. Certainly, World War I, Germany didn't have much of a navy at that time. Even in World War II, Germany didn't have much of a navy. It was the British Navy. But yeah, they remained as a dominant force because of that defeat. Isn't that amazing? And you think about that, that was because of a weather. Had they understood oceanography a little bit better, they may not have found themselves in that predicament and losing all those ships. Notice how this picture down in the lower right, the painting of all the ships. Notice how the sails are in different shapes now. So what I was saying earlier, the Romans and their triremes it's like a bed sheet, and the humans are figuring out, oh, wait a minute, if we shape it this and we, make a jib out of it and all that, then we get more efficient sailing techniques or sailing efficiency. Okay? All right, cool stuff. I think, man, if I was going to be born in another time, it would have been during this time. I would have loved to have been on one of those ships, especially I'd like to have been one of the 18, of course, but like Magellan, just to, this is what I'm talking about in the book. Oh my gosh, it took forever. And as you get near the equator, that's where the doldrums are. So there's not as much wind. So it was hot. They're running out of water, and they're just floating. And you can imagine. I got a job in the Keys right after I got out of grad school, and one of the things we did is we'd go out in a small boat and float, and we had this sensor at the time that we could tell latitude and longitude with, and we were documenting currents. We would just float in the boat, and every hour or half hour, I don't remember what it was, we would write down our position, and we could put on a chart. We'd see we're looking at small little currents that were flowing between the islands and the Keys and all this sort of stuff. But man, this is in the summer. Laying out on the boat now we had a bimini top, but laying out on the boat all day, just floating, you feel like you've been baked all day long. I can imagine what these guys are like. I think that's, if I remember the book, that's where they lost most of their the men, was that trek across the Pacific. So James Cook comes along, England, he's English and all that sort of stuff. He's the fella that we're credited for discovering Australia, Hawaii, the Society Islands, he called them, the Society Islands. He made 3 voyages, eventually dying on the last voyage. I was going to say on one of them. Well, it had to have been the last one. But he was probably one of the first ones we credit with collecting scientific data, right? Things like oceanographic data, like sea temperature, the winds, currents, depths, just taking a rock on a stick and dropping it down and charting the depths and information about coral reefs and their location. He also helped solve a problem of a disease that used to kill a bunch of sailors. As a matter of fact, it used to kill more sailors than being attacked by pirates or by the Loch Ness Monster, was scurvy or a deficiency of vitamin C. Deficiency of vitamin C would occur on sailors, and they would die from scurvy. James Cook used a book said, what was it, sauerkraut? Yeah, he used sauerkraut, which is very high in vitamin C. So his men ate sauerkraut, and they were able to actually wave off the problems of scurvy. It's why a derogatory term for British is a limey. I don't know if you've ever heard that. I don't even know how derogatory it is. It might not be. If it is really derogatory, I'm sorry to use it there if you're British, but it comes from the limes that British sailors would occasionally would have along with them, and they would suck on the lime to get the vitamin C. Sauerkraut would do it too, of course. But okay, now back to this whole thing of longitude. Latitude, it's the position of a star, right? How a heavenly body, where it is above the horizon. That's easy enough. But what about longitude? Dead reckoning. Got to really know how fast you're going. You got to really, have a good sense of the currents and everything. And as I said, the longer you dead reckon, the bigger that mistake is going to become. And then you're running aground when you shouldn't. I remember reading a book about some of the early explorers, and they early explorers would always hire a pilot. The captain of the ship would be the captain, but he would hire this guy who was a pilot. And a pilot used to have a thing called a wheel book, and in the wheel book were little notes that he knew or he got from friends, other pilots, and like, be careful, there's a coral reef just northwest of this area, you know. And if you were a captain of a ship, you wanted a good pilot, had all these little secrets in the wheel book, because the maps weren't worth a darn, and even if they were, you didn't know where you were, right? So it was real important because you didn't want to run aground and you want to get to where you wanted to go. If you're sailing out across the Pacific Ocean, I'd like to know I'm going in the right direction. So it was solved by a guy named Harrison in the early 1800s. It was a prize. There was a contest that the British government sponsored to whoever could solve this problem. And this guy who made chronographs, clocks, a guy named Harrison. Actually, I think he made cabinets. Your book said cabinet maker. In 1837, he came up with a really accurate chronograph. Okay, now a clock, yes, but an accurate clock. Now, your book's got a really good explanation of it, and if you're not afraid of a little bit of arithmetic, math, and geometry, look through Appendix 3, and it'll tell you how you can calculate longitude from your time. But basically the way it is, and I'm not going to go into the math, but the world got together, and by convention, we decided that zero longitude was a vertical line that went through Greenwich Observatory in London, England. I've actually been by there when I went to England many years ago. The Greenwich Observatory, we've decided that spot on Earth, the line of zero longitude runs right through it. And everything to the west is west longitude, and everything to the east is east longitude, right? Makes sense. The way you figure out where you are on the Earth this way, or on the other side that way, is by comparing what time or where. Okay, let me get this right. It's by knowing what time it is where you are. Back up a second. It's when it's noon exactly where you are on Earth. What time is it in Greenwich Observatory in London? Okay, so you're sailing out across the Pacific. When it's noon, you look at, how do you know it's noon? That's real simple. You look up, the sun's directly above you. You run down to your really accurate chronograph and you look at it, and it tells you what time it is in Greenwich Observatory, England, wherever, you know, on the other side of the world. Now, it's not that time where you are, but that's what time it is there, right? That information tells you where you are, west or east. The difference between when it's noon where you are and what time it is at the zero longitude in England, that tells you where you are, west or east. Okay? Sorry, I got a little confused there at the beginning, but take a look at Appendix 3. Even if you're not really good at math, look at it. It's kind of interesting how they figured it out. Now it's all electronic, so it's no big deal. But that's how they figured out longitude. And the importance of Harrison's clock, people have been clocks for many years, folks, was its accuracy. Right, the more accurate it kept time, like not losing seconds. Now think about, this is a clock that's got to bounce around on a ship too. So Harrison figured out a way to make a clock that didn't, get the snot beat out of it, so that its time got all messed up. All something, by the way. What year is this? 1728, 1779. I don't remember what. It's 1837. All something that had already been figured out by Arab sailors, Arab explorers, just lost. Okay, what a shame, right? Okay, there we go. As we move in today, now oceanography encompasses a lot of things. If you want to study oceanography, someone says, "Oh, I'll go to school to be an oceanographer." I go, "What type?" And they're like, "Oh, an oceanographer." I'm like, "Oh, no. There are many types of oceanographers. There are oceanographers that study the geology of the ocean, geological oceanographers. There are those that study the chemistry of the ocean. There are physical oceanographers that study the physical structures, the things that we're going to talk about, the continental shelf, the mid-Atlantic ridge, all those really cool, just incredible things that we're going to talk about in the next few chapters. There's biological oceanographers. A marine biologist would be a biological oceanographer as well. A biological oceanographer might be someone who studies the ecology of marine organisms, because in ecology, we look at the organism holistically, right? We look at the organism in its environment. How does this tagged whale that you see in the little picture there, how does it interact with its environment? Predator, prey, the chemistry of the water, all those things that influence living organisms, right? And so now in this modern day, I mean, you can tap on and follow those sharks, you know, those tagged sharks. You can actually get an app for your iPad or your phone. It'll tell you where, what is the one that my brother-in-law is always, so if Catherine, I think is the name of the animal. I always tell them it'd be funny if you're sitting out on the off Siesta Key, floating on the raft, checking your phone, and Catherine's right next to you. I think that'd be funny. Okay, the beauty of all this, and there's a variety of things. A hydrophone by which to listen to sounds. It's very common, or a very common item used among like marine mammalogists, looking at communication in marine mammals, that sort of stuff. An ROV is a remote operated vehicle, so it's tethered to a ship and they fly with a joystick. So those of you who have an interest in oceanography, who are really good with joysticks and video games, I was on a ship in the Gulf of Mexico where we were looking for the eels that I worked on, and they had an ROV, and they had this young guy. He was my age because I was young too. But he said, "Oh yeah, he goes, I was a video game addict. You know, of course back then this was like Pong, but he was flying that thing around with those joysticks." Another thing they can do, these really cool kind of stuff, is they can get these meters, these like a current meter or nutrient meter, which reads the nutrients, and are attached to the bottom. And they can either, be it's got like a USB port if you think about it, but they can also be freestanding. They don't have to be connected to anything. And they'll stay there and collect data for, a year or two or something like that. And every once in a while, they'll raise themselves to the surface. And above the surface, an antenna will stick up, and they'll relay information to a satellite. So you can get information remotely from these sensors. And it can also be real-time, too. In some cases, they can do real-time relay. So you can look online now and say exactly what the water temperature is. Look on the NOAA website. They have a current buoy conditions, and you can tell what the current conditions are at a buoy out in the middle of out off the coast in the Atlantic. Isn't that neat? That's what citizen science is all about. There's all these neat citizen science projects that folks can get involved in, where you can actually help process simple amounts of data with stuff like that. If you're interested in that citizen science kind of stuff, let me know, and I've got some websites you can go to. So we got submersibles. Did a submersible dive. Awesome. Had such a great time. And this thing, I saw this the other day on TV. This is really cool too. I can't remember what the name of this is. It's FLIP, which stands for something. FLIP. Floating Laboratory or something like that. I don't remember. But it's a ship. They take it out to wherever they're going to do their sampling, and then they tip it. So this part sinks, and the bottom of the ship comes up, and this is a floating laboratory. This thing floats in the water. So it's floating in the water, and they can go down in these areas and collect samples, go in the middle, and they have these laboratories in here. But what's cool in the show I was watching, like tables and the urinals and all that stuff, it's all on pivots. So this thing rotates, that the chairs and everything rotate with it. It's really kind of interesting. And down on the Florida Keys, actually, you can do this on Key Largo, underwater habitats. So if folks could live underwater, there'd be living facilities and laboratories, and they could, this would be good for things like mariculture, doing research on mariculture. Mariculture is agriculture in the sea. So, growing things that would, in the ocean. Can't think of any better job to have stuff like that, right? Okay, so now let's kind of step back out of oceanography, and let's look at science in general. Let's talk about how scientists answer questions. Let's talk about how scientists attempt to get at the truth, if there really is such a thing. You really never can get at the truth of something, right? The truth is perception, and there's always human bias. But in science, what we try to do is remove as much human bias, remove as much of our perception from reality. And again, that's a really slippery slope. So, you can understand what I'm trying to get at here. The scientific method, even though it's called the scientific method, to me, it's really nothing more than kind of the way we think. And in its simplest form, on this chart that you see here, it's you make an observation, You come up with a question which you answer with a hypothesis, and then like most human beings, we want to know if we're right or wrong. So you test that hypothesis, and then if that hypothesis is right, after a number of tests, you can come up with a theory. Okay, so now again, that's good for answering questions about migration patterns of gray whales. It's good for answering questions about plankton productivity in the North Atlantic. It's good for answering questions about are the galaxies moving away from us or coming towards us. It's good for answering questions on, can I beat that yellow light as I'm driving my car, right? Isn't it? So the scientific method is really nothing more than an outlining of the way your brain processes. I see a yellow light. I think I can beat it. I didn't beat it because I got in an accident. My theory is next time I'll need to be moving faster, be closer, or whatever the case may be, right? That's just the way your brain works. Okay, so now let's take that basic outline, observation, hypothesis, testing, theory, and put it in a little more expanded framework. Put a little bit more, talk a little bit more about the details. So that's why this chart has a lot more on it. So let's move into this. Again, at the top, there's the observation. And you come up with a question. As I mentioned, it could be observation, gray whales are migrating. Question, why? Why do they migrate? Well, from there, from a question, you're going to come up with some reasonable answers, some reasonable guesses. That's what they are. They're guesses. A hypothesis is a guess, but it's not just a harebrained guess. It's a guess that has some reasonability to it. For example, if you were standing on the beach at night as the sun had just went down and you looked off into the sky and you saw a bright light, you could think it was the landing lights of an aircraft, right? You could think it was a star. Could have been maybe it's a helicopter. I guess that's an aircraft too. It could be a planet. A fifth hypothesis is it could be a UFO, right? Nobody has ever proven that UFOs don't exist. Nobody's ever proven they do exist, as far as I'm concerned, and lots of other people. But nobody's ever proven they don't exist. So it could be a UFO. My take on UFOs and their existence is this. When I was a kid, there will always be these black and white, grainy photographs of UFOs. And it always looked like a Frisbee in somebody's backyard. It looks like obviously what it was, which was a fake. In this day and age, where everybody and their brother has got a bazillion pixel camera on their phones attached, almost growing out of them, nobody as of yet has got a good shot of UFO. So to me, I would think with all these good cameras and everybody having them all over the world, somebody would have got a really good picture, but nobody has so far. But anyway, it might be a UFO. But as we go through experimentation, and that's kind of what these next three steps are talking about, we reject hypotheses. We might do some experimentation and look into, what are the odds that it's a UFO? And really, that's what hypothesis rejection is all about. That's where the statistical testing comes in, folks. That's what statistics does. Statistics tells you the odds that what you're seeing are happening is really, truly happening. It's not some random event. So you're playing Monopoly and you roll double sixes twice, right? Wow! It must have been because I was thinking about double sixes twice. No, it's random. It's luck. So you go to the lotto, Florida State Lotto, and you play your birthday, your mom's birthday, your dad's birthday, and you win. No, it was luck. You can play 1, 2, 3, 4, 5, 6. You can play those numbers and have the same exact chance of winning as if you played all these random numbers, okay? So that's what statistics does for you. And so through statistical testing, it's about probability. What's the probability that that light is a UFO? 1 in a bazillion? I know there's no number bazillion, but come on now. What's the probability that it's the landing lights of an aircraft? Well, let's see, there's an airport right behind me. Pretty doggone good, right? So, until we see it fly over, we can make a prediction that based on these probabilities that that's probably an airplane. And then as it flies over, we could confirm our prediction. And if that was wrong, we might have to modify our hypothesis. Because you're not always right the first time out. But the goal behind making a hypothesis and testing it over and over again is to make a prediction. I'm going to tell you right now, when there's a light out in that distance at this time of night, traveling in this direction, that's a 99.9% possibility that's an airplane coming in for a landing. Now, maybe 0.00000 blah, 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 1% of the time it's a UFO, but if I'm going to bet money, I'm going to bet money it's an airplane. That's what statistics, it's betting money. It's being able to make predictions. And statistics helps us differentiate between things that really truly are happening and randomness. You know, if you flip a penny 100 times, statistics says it should come out 50-50, right? Probability says, but it doesn't. It may come out 51-49. Does that mean that penny's got something wrong with it? Maybe. Chances are, though, it's just random. Okay? Now, once you get a hypothesis tested enough times, then you can make a theory. So this argument that I hear a lot from folks, not a lot, not really, not as much as I used to anyway, that, well, it's only a theory, that's really not understanding what a theory is. A theory is not just, it's just a theory. The Earth rotating on its axis, day, night, is a theory. But when have you known it not to happen? Okay? It's that probability thing again. So if you test your hypothesis, and many times you test it, it comes out your predicted answer each time, or most all times, you can say in general, now that could be a star up there, but in general, it's probably an airplane. And it could be a star, more probability than it could be a UFO, right? See how that works? That's what we mean by a theory. As it says right there, they're supported by large amounts of evidence. The theory of evolution by natural selection, Darwin's theory, is supported by large amounts of evidence, folks. It's not just some harebrained theory. Okay, now, when you're doing an experiment, all right, so you're testing something in something, you want to make sure that you're controlling for all the variables. And you want to make sure that you have something called an experimental group and a control group. And the control group is the same as the experimental group, but the only thing different is the variable you're testing. Okay, now that sounds like a lot of mishmash. Let me explain it to you with an example. Let's imagine that you worked at a pharmaceutical company that had come up with a drug that would cure folks of diabetes. As of yet, we do not have a cure for diabetes, all right? And you want to test that. But we also know the power of the human brain. And so if you think you're getting a drug that may be curing you of diabetes, you might show some quote-unquote improvement in symptoms of diabetes, even if you're not really getting the drug. You know what I'm referring to? You know what that's called? Right? Placebo effect. One of the best examples I had was years ago. I remember there was this thing, it was on TV and the magazines. If you suffered from seasickness and you wore this band around your wrist that pushed on the center part of the inside of your wrist and put pressure on that pressure point, it would prevent you from getting seasick. It's manure. There is no way that prevents you from getting seasick. But if you wear that thing on a ship and you think it prevents you from getting seasick, just you thinking that might be enough, because seasickness is a lot in your head. It's not all in your head, but it's a lot in your head. When you start, I feel like I'm going to get sick, well, then, that's where the cycle starts, right? So back to my diabetic folks. So here's how you solve that. In room A, we have 100 diabetic patients. In room B, we have another 100, and they're all similar in terms of age, otherwise health, that sort of stuff. We're trying to make them as similar to each other as we possibly can. Both members, 100 in the A and 100 in the B. Every day the orderly goes into room A and he gives everybody in room A, which is the experimental group, he gives them a pill with the drug that you're testing. Every day an orderly goes into room B and he gives those diabetics a pill, but guess what? There's nothing in it. It's just a placebo. It's the control group. Okay. Now, 6 months, a year down the road, if 53% of the people in room A show marked improvement in their diabetic symptoms, and one person in group B You got to look at the probability again and expect that the difference between the two has to be the drug. Everything else is the same. Everything else is the same. They're the same diabetic patients, essentially, same, as I said, otherwise health conditions. The only difference is one gets the pill and one doesn't. You always have to have a control group because you got to make sure that when you see a result, it's because of something that you have taken into account and not something that is unforeseen, right? A friend of mine was doing work on dolphins out in the Indian River years ago, and I was piloting the boat and assisting her with collecting her data. She was doing her master's degree on this, and the question was, does the influence of humans, or does the presence, excuse me, the presence of humans in the Indian River affect dolphin behavior? And folks in the past have actually categorized dolphin behaviors. There are a fellow named Randy Wells, if you're interested, looking at Sarasota dolphins, has actually categorized different types of dolphin behaviors. Chuffing, milling, traveling, right? Those are all dolphin behaviors. So what she did is she would go out and we would follow dolphins around and we'd record what the behaviors they were doing. Well, she needed a control group. You see, if she was going to say that the presence of humans affected dolphin behavior, then what's the dolphin behavior with the lack of humans? Where do you find dolphins hanging out where there aren't any humans? Now, in the Indian River, that's not the case. There's humans everywhere. There's commercial fishermen, crab fishermen. There's recreational fishermen, recreational swimmers, etc., right? Boaters. So what she was able to use as a control, wasn't a great control, but it was better than nothing, was found that the dolphins in the Indian River area, the Indian River Lagoon system, kind of stayed in the same area. So what she used for control group were the dolphins that were found on the restricted area of the Indian River Lagoon, down by Cape Canaveral, down by the Space Center. Not there's areas in the water there that you can't go without a permit. So she got a permit, and we would go out onto those waterways and record that dolphin behavior. So it wasn't exactly a perfect control because there were still some humans there, but not as many as are out on the regular part of the river. See what I mean by a control, though? Does that make sense? All right. Any questions before I go on? Plenty of information online if you need more about this whole idea of experimental and control group. Plenty of videos on YouTube. Plenty of great little interactive exercises. I mean, I could go out and link to them, but there's so many. If you went into Google, you'd find tons of them yourself. So, if you do have troubles finding something like that and you want to take a look at it, let me know and I'll get one for you. Okay, reasoning. How do we reason stuff here? Now, this trips up even the most seasoned scientists sometimes. If you ask them very quickly, what's the difference between inductive and deductive reasoning? Even myself, I have to go, ugh, because the name is almost kind of an opposite of the way it is. All right, inductive reasoning. In inductive reasoning, we say the logic flows up. Right? Now, that's not confusing enough. Obviously, there's nothing flowing up. But what we mean by that is that in inductive reasoning, what you do is you make repeated observations, and that leads you to a generalization. Okay? Now, the opposite of that is when the logic flows down. And that's when you take a generalization to make a specific prediction. All right, now, I know that might be a little confusing, so I think an example will help. Let's use a little bit of inductive reasoning to answer a question. Let me go to the next slide. All of these critters here are mammals. They're all considered mammals. Based on the picture that you see here, based on the picture, these are your observations, okay? Based on the observations that you can make here, what is the one obvious distinguishing characteristic that lumps all these organisms together as mammals? What do they all share that makes them mammals? If we call in all these mammals, we say they're all mammals because of what that we can see in this picture. Fur. Yeah, that's right, Danielle. We see hair, don't we? Now, you probably already know that. You probably, so I'm using a very simple example, but in more complex form, that's what we're doing. We've made several observations: the cheetah, the Iberian lynx, the lion, the chimp, the striped hyena, blah, 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 blah. They all got hair. These are all mammals. So we're going to use repeated observations, right? A dingo, a hippo, a giraffe, a ring-tailed lemur. We're going to use repeated observations to make a generalization. We're going to do some inductive reasoning. All of these critters that I've looked at have hair. Therefore, mammals have hair. See, now I wrote that in right here. Mammals have hair. We've used inductive reasoning to come up with a generalization. Many times, inductive reasoning statements have the word all in them. All mammals have hair. They're very general. If all birds, oh, do they? Yes, all birds have feathers. Okay, those are generalizations. Now, we can then use, and we use these things interchangeably, inductive and deductive reasoning, but we could use that inductive statement, like all mammals have hair, to make a prediction. So we're then engaging in deductive reasoning. So the logic flows down. I put a little quote there. If a species has hair, it is a mammal, right? Now, you see how the logic flows in different directions here? In inductive reasoning, we look at isolated, or not isolated, but repeated observations and say, every time I see A, it's a B. Every time I see hair, it's a mammal. And then you can turn that around and say, then I shall deduce. That's kind of how I try to remember, because that's how you would say, I deduce, and what you're doing when you're deducing is you're making a prediction. I deduce that as I'm walking around through the jungles of Borneo and I find this unknown critter that nobody's ever seen before, but it's got hair, then it's a what? If I find some unknown critter crawling around the forest of Borneo and it has hair, then nobody's ever seen this critter before. Nobody knows what it is. I don't know exactly what it is, but because it's got hair, I know it's a what? Stick with me, folks. A few more minutes. Yes, it's a mammal, Ace. Thank you. Yes, it's a mammal, right? Easy enough. Oh, here's a critter. Two of them. Do they have hair? Does that humpback? Yep, that's humpback. Does that humpback have hair? Those killer whales have hair? No, they don't. Then they're not mammals, right? Oh, what's Professor Clark trying to do? Really screw with my brain before the class ends? No. You got to keep in mind that the world is never black and white. And you got to keep in mind that when we say things like all mammals have hair, we might want to add that at some time in your life. So just because your dad's gone bald doesn't mean he's no longer a mammal. Whales and killer whales do have hair. Not when they're adults, but look at this right there. See those little spots? Those are called rostral hairs. Remind me in class next week, and I'll show you one. This is a killer whale calf at SeaWorld when I worked there. And they have little hairs near their nose, near their rostrum, which is nose, that they use to sense. That's not how you spell nose. They use to sense where they are next to their mom. Now, hair is not good for swimming. It's a hydrodynamic drag. Olympic swimmers shave their bodies, don't they? After a while, those rostral hairs fall off. I was lucky enough, though, that one was very loose, and the trainer was able to pluck it off there and gave it to me. So I have a little tiny rostral hair. Usually you don't see them. Okay? So keep that in mind. If you take my Bio 2 class, if you do take Bio 2, we talk a lot more about those kinds of exceptions to things that things that we assume. All right? All right, I got a few more minutes. I want to do one more topic, and then we'll call it a day. I got 4 more minutes. I want to talk to you about how life began on Earth. Okay. Well, biogenesis, the beginning of life on Earth. One thing that's interesting is there's some theories that have come out recently that I've been hearing about that suggest that life may have begun on Earth more than once. Began, went extinct, began, went extinct, began, went extinct, then began and stuck. And that was what happened 3.5 billion years ago. Speaking of 3.5 billion years ago, this is some of the earliest evidence of life. These are fossilized bacteria from 3.5 billion years ago. Now, one of the things you got to keep in mind when we talk about how life may have begun on Earth how we went from non-living to living, is the Earth was very different back 3.5 billion years ago. It was a lot of volcano, a lot of what we call a lot of a reducing atmosphere. And even though the word is reducing, in chemistry, reducing actually means building up. So back during this time on Earth, the environment was very conducive for building complex molecules. And that's really what happened. That's what living organisms are. Organisms are a built up complexity of molecules, right? Water is a molecule, but everything in your body is a molecule. So we're nothing more than a chemical reaction, a very specialized chemical reaction. So one of the theories, and it's actually been shown you can do this in the laboratory. Back in 1952, a couple of guys named Miller and Urey set up this experimental setup. This will be the last thing that we talk about. So follow the numbers down here. In one part of their little chemistry setup, they had some water, and they put some heat underneath it in order to get the water to evaporate. So that's the ocean, and the evaporating water is making the clouds. They then injected gases. Now, look at those. You're thinking, holy cow. But back in the early Earth, there wasn't any oxygen. But there was a lot of carbon dioxide, a lot of methane, a lot of hydrogen sulfide, a lot of gases that are known in that chemical term to be reducers, to help build molecules. Now, in order to build something, you need energy. Well, the electrodes would have simulated lightning. All right? And there was lightning because volcanoes can create lightning. So there was lots of volcanic activity, lots of lightning. The lightning was the energy. Then the water vapor that collects would be the rain. And what they found, if you let this cycle many times, you can actually begin to create what's called organic molecules. Now, I don't know how much chemistry you all have had, but organic molecules are molecules that are generally associated with life. A carbohydrate, food, starch, is an organic molecule. Proteins are organic molecules. DNA, your genetic code, is an organic molecule. All right, so the very beginnings of organic molecules, it is possible. You have to go back to that probability thing we've been talking about to see how probable, but it is possible. And as I said, this has been recreated, and folks have been able to do this in laboratories, make these organic molecules. That's a long way from an organic molecule to you and I, but it is at least a starting step. All right, folks, I didn't finish the chapter, but I'm pretty close. We'll finish it when we get together on Monday and talk again. I'm going to go ahead and stop the recording now.